Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 10 on the volumes of pyramids and cones. Now in our last lesson we looked at the volumes of right prisms and of cylinders, and I highly suggest that you see that lesson if you haven't already, because we're going to be building on that in today's lesson on pyramids and cones. Let's get right into it. Alright, so the volume of a pyramid. Now pyramids and cones have volume formulas that are easy to use, but somewhat of a mystery until you reach calculus. We will explore the volume of just one pyramid and see the relationship that ultimately holds for all pyramids and all cones. So let's jump right into it. Exercise number 1. Consider a cube that has side lengths of 2 centimeters each. The center of the cube is located and segments are drawn to each of the 8 vertices of the cube. This creates the pyramid whose volume we're going to explore. So again, let me just make sure that we understand this. You know how we find the center of a regular polygon? Well, the same idea, right? If I took a cube and I connected that vertex with this one and that one with this one, etc., I would locate at their intersection point the center of this cube, all right? And then what I'm doing is I just want to explore what the volume of this particular pyramid is, because we can actually come up with its volume based on just knowing things about the volume of this cube and how many of those pyramids fit in the cube, etc., etc. So let's start off really easy in letter A. What is the volume of the cube? Include appropriate units. All right, this should be no issue. Why don't you go ahead and figure out the volume of the cube and then we'll move on from that. All right, well, the volume of any right rectangular prism, right, the volume of any of them is the area of the base times the height. Of course, in this case, that's going to be 2 centimeters times 2 centimeters. That would be the area of the base times another 2 centimeters. That would be the height. And therefore, we have 8 cubic centimeters. And never forget what that means, right? It means that if I took a little cube that was 1 centimeter by 1 centimeter by 1 centimeter, 8 of those things would fit in here. You can probably even visualize them, right? There'd be 2 stacks of 4. Real simple. Okay, now let's start to think about the volume of that pyramid compared to the volume of the cube. Actually, let me just leave it like that for now. Letter B. How many of these pyramids would fit into the original cube? Why? Use this to determine the volume of the pyramid in simplest form. All right, so I want you to pause the video right now and think to yourself, if I took this particular pyramid, right, and I kind of put it up here and I started to fill things in with this pyramid, how many of them could I put into that cube? Then, once you figure that out, right, then obviously you can just take the volume of the cube, divide it by how many of the pyramids fit into the cube, and that will then be the volume per pyramid. Pause the video now and see if you can figure that out. All right, well, it's going to be 6 of them, right? And it's going to be 6 of them because for every one of the faces of the cube, right? And the cube's got 6 faces, you know this, right? If you take a die and you roll it, it's got 6 sides, 6 faces, right? For every one of the faces, there's a cube, right? Or there's a pyramid, right? There's one down here. There's one that kind of sits in from the top. There's one that I could shove in from the right, one that I could shove in from the left, one I could shove in from the front, and one that I could shove in from the backs. So there are 6 total pyramids. 6 total pyramids fit in the cube. And I'm going to say 1 per face. So the volume, right, is going to be 8 cubic centimeters divided by 6, and I can reduce 8/6 so that I can say that each one of those pyramids has a volume of 4/3 cubic centimeters. 4/3 of a cubic centimeter. All right, or 1 1/3 cubic centimeters if you like, you know, that's fine too. But please make sure that you understand why there's 6, okay? Now, letter C. The pyramid fits inside of a prism that has the same base as before and a height of 1 centimeter. What fraction of the prism's volume is filled by the pyramid? Fill in the missing fraction in the equation below. Now, before we move on, I just want to make sure that you understand what's going on here. I literally took my original prism / cube and I sort of sliced it off right at the top of the pyramid. All right? And the reason why is that I want to understand how the volume of any pyramid relates to the volume of a prism that has exactly the same base as it and exactly the same height as it, okay? So therefore I had to cut that thing down. Now first, let's talk about the volume of this new prism, right? So the volume of the prism, right, is going to be 2 times 2 times 1 now, or 4 cubic centimeters. Right? That's the volume of the prism that this pyramid just fits into. Now, we know that the volume of the pyramid, we just figured that out up above, is 4/3 cubic centimeters. But I hope you understand that, of course, 4/3 is the same as 4 times 1/3, right, by definition, and is the same as 1/3 times 4, right? So the volume of the pyramid is 1/3 times the volume of the prism that it sits inside. And I bet you can almost see that, right? If you think about this empty space over here and over here, those two pieces of empty space would actually sum together to be one of those pyramids. And then this empty space back here and this empty space back here, that would actually sum to be another pyramid. So we would have 1 pyramid, 2 pyramids, and then the one that's shaded, 3 pyramids. So that pyramid is taking up 1/3 of the volume of the prism that it exactly sort of has the same base and height of. So the volume of the pyramid is 1/3 times the volume of the prism. Now, I bet if I took a survey and I said, hey, how many people would think it was 1/3 or 1/2 or 1/4, most people would probably assume that it was 1/2. Because, you know, a pyramid seems like it's a triangle, right? And a prism sort of thing seems like it's a rectangle. And, you know, the area of a triangle is 1/2 the area of a rectangle. But here the weird thing is that the volume of a prism the volume of a pyramid will always be 1/3 times the volume of the prism that has the same base shape and the same height. And it's really kind of cool. The relationship from exercise number 1 is remarkable in that it holds for all pyramids and cones, as the following formulas will suggest. So the volume of a prism is its base area times its height. The volume of a pyramid is 1/3 its base area times its height. The volume of a cylinder is pi r squared times h, and the volume of a cone is 1/3 times pi r squared h. So really, we've got exactly the same formulas that we worked with in terms of prisms, right? We find the area of the base, we find the height, and we find their product. We have to throw in a 1/3 factor, all right? And that's annoying because, of course, fractions, right? Not just fractions, but fractions that also involve pi, and a fraction of 1/3. I mean, they couldn't even make it like 1/2 or 1/4, right? I'm not sure who they are, but let's complain to them when we have a chance. Let's take a look at exercise number 2. The Great Pyramid of Giza in Egypt has a square base that measures 756 on a side and a height of 481 feet tall. By the way, this is true. Look it up on Google. To the nearest million cubic feet, that's right, million cubic feet, what is the volume of the Great Pyramid? All right, well, this is really cool. And again, you could imagine this pyramid sitting inside of, a prism, right? That is not a prism that is 756 feet this way, 756 feet this way, and 481 feet this way, right? And this thing's going to occupy up 1/3 of that space. So it's really, again, pretty easy. If we were doing the prism, right, the prism, we'd have 756 times 756, that would be the area of the base, times 481, that would be the height, and the big difference now is we have to throw that 1/3 in. All right, what I'd like you to do right now is pause the video, come up with what this volume is, and maybe just as challenging, round it to the nearest million. Pause the video now and go ahead and do that. All right, let's do it. Here we go. Maybe I'll break out of this really quickly because I love the size of this number. It's huge. All right, so 1/3. Let me get my fraction in there. Might as well. 1. Ooh, it worked that time. 1/3 times 756. Actually, maybe put the times button in there. 756 times 756 times 481. Yep. 481. This is going to be a large number. And we have 9,163,000, right? Oh, sorry. 91,636,272. 91,636,272. Let me write all of that down. Actually, let me go back to my handheld only, now that we've gotten a good look at it, and then we'll do the rounding. All right, so all of this is 91,636,272. And to the nearest million, which by the way makes sense, right? Because if these dimensions are a little bit wrong, right, which they are likely to be just a little bit off, then that will make a huge difference here. And quite frankly, right, it's impressive enough to just say 92 million cubic feet, right? Clearly, if we had a population of a country that was 91,636,272, and somebody said, hey, what's the approximate population of the country? And you said 92 million, that would be pretty darn accurate, right? Big volume, big volume. Would not want to try to move that thing. Okay, let's take a look at exercise number 3, where we combine two shapes. A cylinder of solid material with a radius of 4 inches and a height of 10 inches has a cone with the same height, same radius and height removed from it. What is the volume of the remaining material? Round to the nearest cubic inch. All right, well, I think it's probably no surprise that what we're going to want to do here is we're going to want to find the volume of the cylinder, and we're going to want to subtract out the volume of the cone. So what I'd like you to do is play around a little bit with this problem. It's really just plugging numbers into a formula. See what you can find. All right, well, I'd like to keep this calculation going right here, right? So the volume that remains will be the volume of the cylinder. Well, what's the volume of the cylinder? That's pi, right, times 4 squared times h, right? So it's the area of the base, right? Pi r squared times the height, which is 10, minus, right, exactly the same thing except with a 1/3 sitting out front. Right? So we've got exactly the same kind of expression, pi r squared h, but with the 1/3 sitting in front of the cone. And now again, the thing that is really, really nice is I can take my calculator out. I don't think I'm going to make it big this time. And I can just type it all in at once. So I'm going to do pi times 4 squared times 10. There's the volume of my cylinder, minus, get my fraction bar in there every time, 1/3. Again, don't forget the pi's. That is the major mistake that people will make in these types of situations, right? 1/3 pi times 4 squared times 10. And what do we want? We want it to the nearest cubic inch. That is going to be 335 cubic inches. Now, as always, there is absolutely nothing wrong with figuring out the volume of the cylinder, writing out maybe some decimal places, figuring out the volume of the cone, writing out some decimal places, and then doing the subtraction. But this is really handy because we don't really then have to think about rounding until our final answer. And we certainly don't have to think about, oh man, this thing is so messy and this is so messy and now I gotta type in all the decimals correctly, right? That can be a challenge, and of course it can lead to errors. So let's keep going and take a look at one final problem. All right, exercise number 4. A pyramid is constructed from a cube as shown below. Point C is the midpoint of edge AB. If the cube has a volume of 216 cubic centimeters, then, letter A, what is the volume of the pyramid? All right. Well, I'd like you to play around with this one. I think this one's a little bit challenging, all right? And let me suggest that the first thing that you want to do is figure out how long each side of the cube is. Pause the video now and see if you can figure out the pyramid's volume. All right. Well, the volume of any cube, right? The volume of any cube is literally its side length cubed, and we know that that's 216 cubic centimeters, right? Now, if we need to figure out what the actual side length is, and we can't sort of work it out by just thinking about numbers and what it possibly could be, we can then always use the cubed root option on our calculator. All right, so I can bring my calculator out. Right next to the square root is a generic root button. I just need to put a 3 there to tell it that I want the cubed root of 216, and that gives me a side length of 6 centimeters. So this cube has side lengths that are 6 centimeters each, and I'm gonna write that down just so that we have it. Now, let's think a little bit now about our pyramid, right? Now, for our pyramid, there's a variety of different ways that we could go about doing it. But it's probably easiest to assume that we're going to use this shape as our base, right? I mean, it's sitting on it anyway, so why not, right? Now, that is a triangle, right? And it's a triangle that has this length of 3, right? Because C is the midpoint of this side. So it's got a length of 3 here, and it's got a length of 6 here. And even though it may not look like it, it actually is a right triangle, right? It's a little bit hard to tell that, but it must be a right triangle because, of course, this side of the cube and that side of the cube are perpendicular to each other. So the base actually looks like that, in which case the area of the base is 1/2 of 3 times 6, which is 9 square centimeters. All right, so the area of the base is 9 square centimeters, and the height that's perpendicular to that base, the height always has to be a perpendicular dimension to the base, is 6 centimeters. So ultimately, I can say that, the volume of that prism is the volume of that pyramid is 1/3 times our base area, times our base area times our height. All right, and that ends up being 18 cubic centimeters. Yeah, that's right, 18 cubic centimeters. Fair enough. Last part of this problem, letter B. What fraction of the cube does the pyramid occupy? Express as a unit fraction. And a way to think about this is almost like, we're going to have 1 divided by something, and that something is how many of these pyramids I could shove into this overall cube. See if you can figure out the answer to that. Well, if I want to know what fraction of the cube does the pyramid occupy, I'm going to take the volume of the pyramid and I'm going to divide it by the volume of the cube, right? So my fraction is going to be the volume of the pyramid divided by the volume of the cube. That's going to be 18 cubic centimeters divided by 216 cubic centimeters. Most of the time I hate how this calculator reduces things like this to fractions, but this time I love it. And I'll get 1/12. Right? 12 of those pyramids could fit into that 1 cube. And again, it's weird. Doesn't exactly seem like that, right? And it would probably be one of those tricky little puzzles where you'd be like, okay, I got to turn it this way and that way and whatever. But 12 of these can fit in that entire cube. All right, let's wrap this up. So today, we really looked at 2 shapes that are more or less the same, the pyramid and the cone. And what we found with both pyramids and cones is that their volumes are related to the prisms and the cylinders in which they can just fit, right? And basically, right, every time they have a volume that is exactly 1/3 times the volume of the prism or the cylinder that they can fit in. Now the great thing is, right, you have to then use those formulas that you already learned about with prisms and cylinders. You just have to toss a 1/3 in front of them. These problems can obviously get awfully messy, especially when you're talking about a cone and the number pi getting thrown in. But as long as you take your time with the formulas, double check them when you put them into your calculator, you'll get the correct answers. Get some practice on that on the homework. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.